In this video, we're going to be talking about the two newest models of the atom, which make up what we call modern atomic theory. Just like the last video, you're going to need the same set of notes. You're going to need something to write with. And once you have those ready, let's go. Now, the first thing I want to go over is I want to go over an experiment that was performed by Niels Bohr. And before I get to the next slide, I want you to think about what would happen if you took sunlight or you took a flashlight and you shined that light through a prism. What would happen? Well, you'd get a rainbow, right? You get what's called a continuous spectrum. One color bleeds into the next, into the next, into the next, right? Your Roy G. Biv in order. Now, if we change that sunlight into light from a pure element, we get something slightly different. And here's what we get if we use hydrogen, right? Hydrogen vapor is electrified, causing it to create light. You pass it through slits, so you have just narrow beams of light that you can control. Put that through a prism, and you get 4 lines. You don't get a rainbow, you get just 4 lines. And those are the 4 lines shown below. Why is that? Well, one of the things that happened between the nuclear model that Rutherford came out with and this new experiment, so one of the things that came to prominence over those years is the idea that energy is what we call quantized, meaning that energy can only exist at certain values and can't exist in between them. The best way to think about it is, let's imagine you want to get up an incline. It doesn't work like walking up a ramp where you have this nice gradient to go up. It's more like walking up a set of stairs, where one step is an energy level, then the next step is a few inches higher, that's another energy level, then the next stair is the same number of inches higher, that's another energy level, and you climb it like that. Now, on our scale, those stairs are so small we don't even notice. They look like a ramp to us. But when we start talking about on the scale of electrons, these become very large steps. All right, so this is the experiment that led to the Bohr model of the atom. This is the one you're familiar with from last year. The way that this works is that we took Rutherford's nuclear model, where you have the nucleus in the center, and instead of each electron having its own orbit around the nucleus, like individual planets around the sun, electrons can only exist at certain amounts of energy, what we call energy levels or energy shells. All right, so what we have here is we have our atom, in this case is a carbon atom. The first 2 electrons occupy the first energy shell. The next 4 electrons occupy the second energy shell. Electrons can only exist in those exact shells, and they can't be anywhere else, right? So it can either be in the first, second, third, fourth, or fifth shell, but it can't exist between shells. Higher energy electrons tend to be farther away from the nucleus than lower energy electrons are. Right, so the lowest energy electrons, the ones that are most attracted to the nucleus, are the ones that are closest to the nucleus. The higher energy electrons, the ones that are less attracted, are farther away. And the only way you can transition between different shells, right? So one of the electrons in that first shell can jump into the second shell, but in order to do that, it has to gain energy in the form of a photon. And that photon has to be the exact energy difference between the 2 shells. Similarly, if I had an electron like the 4th energy shell and I wanted it to drop down to the second shell, it would have to lose energy in the amount equal to the exact difference between those 2 shells. So this is the Bohr model. This is the one you're familiar with the different rings. Right? So if I were to describe this is shells. This was discovered through hydrogen gas. And do we use the Bohr model today? Well, ask yourself, did you use this model last year in biology when you were drawing your atoms, right? You drew the concentric circles and put in your electrons. So yeah, we still use this model today. In fact, most of what we do in this class will be done using the Bohr model because it provides enough useful practicality for you without bogging you down in minutia. Right? It's not the current model, but it works well enough for what we need, so we use it. Speaking of the current model, that gets us to what's called the quantum mechanical or quantum model or electron cloud model, whichever name you want to attribute to it. This is the work of Erwin Schrödinger. Erwin Schrödinger is not a chemist, he's not a physicist, he's actually a mathematician. What he did was he modeled the energy of electrons and the electron-electron repulsions, right? So the energies of all those things using what's called statistical mechanics. So he came out with a statistical equation to describe how likely it is to find an electron at any given point in space around the nucleus based on its energy. Areas that have a very high probability make up what's called the electron cloud. The more dense or the darker the electron cloud is, the more likely it is to have an electron in that location. So if you see this one right here, this is the diagram for hydrogen. The highest probability of finding an electron for hydrogen is close to the nucleus in a circle. And as you go farther and farther away, the probability decreases. For other elements, it may have a shape kind of like a dumbbell or like a flower or something like that. Each electron works individually. This is our currently accepted model of the atom. Now, this, like I said, so since it's currently accepted, this is the one that we use, but we're not going to be using it all that much in this class because it's a lot more math and a lot more crunchiness for not a lot of benefit. So we're going to use mostly the Bohr model because it gets us like 95% of what we need without bothering to bog us down at all. So these are the different models of the atom that we're working with. They're currently working to see if we can find new models of the atom based on new things that we've discovered since the 1920s and 30s. Right, but that's it for atomic models. I will see you guys next time.